Right, hello guys. So we went through the basis of what control reversal is, and this idea that the aileron, not the elevator, the aileron gets less and less effective with forward speed until a point at which it has no effect, and then beyond that the ailerons work in the opposite way to what you're expecting. So we can actually take the model that we developed for divergence. Let's go back and look at our divergence model here. I'm trying to think where our divergence model was. Here. We're going to look at our divergence model and we're going to modify this to include the elevator, and we're going to then work out, can we determine the control reversal speed? Okay, so before we get there, we're going to do a little bit, we're going to set up the problem. We know that the aileron is designed and is desired to produce an increment in lift, which we call delta L. And we'll say that delta L is going to be equal to whatever the actual increment in lift is due to the elevator deflection. So dL by d delta A. I keep messing up at aileron and elevator. I can hear it, sorry. I'm only talking about ailerons in this class, but I will confuse them at times when I'm speaking. Okay, so this would be the rate of change of the lift with the aileron deflection multiplied by the aileron deflection, and then we've got to account for the reduction in lift due to this torsional twist. So let's put the parts in this equation. This is the rate of change of the lift in our section due to aileron deflection. And then we've got, this is just the lift curve slope in dimensional form. Okay, and the reason I put this one in green is because we need to develop an expression that gives us this torsional twist. So this is just going to be a number. Generally, we'll do this in coefficient form anyway. This will be a number, and this will be the change to the slope of the change to the lift coefficient with the elevator deflection. Okay, so it's going to be a number. We know it's going to be probably a small number, an order of magnitude lower than the actual lift curve slope of the aerofoil itself. This is then just the elevator deflection. That's going to be just how much we've got the elevator deflected by. This is the lift curve slope of the aerofoil itself, which will, if we're looking at this in coefficient form, we'll just say it's 2 pi. And then this bit here, the torsional twist, is what we want to try and determine. Okay, so we've got these two different parts here. This is sort of the ideal. And then this bit over here is the aeroelastic effect. Right, I'm going to draw the same model that we effectively had for the divergence case. I'm going to include the elevator in it as well now. I'm going to take my time with this. Okay, so I've drawn now, I've got the same torsional spring that we've got here, which has got the stiffness KD. I've put on here the increment in lift and I've put the increment in pitching moment, both dimensional. Now, the convention for moments are that they are positive nose up, or sorry, the convention for pitching moments certainly is that it's positive nose up. We know that this is going to produce a negative moment, but I'm still going to draw this as a positive one on here, and we'll just make sure that we have a negative number. So we've got this expression up here. We could rewrite this in coefficient form. So before we had dl by d delta A, I'm now going to have dcl by delta A. Okay, so that's just taken the same expression we've had before, rewritten it in coefficient form. dcl by d alpha is just the lift curve slope, which we say is A. This is still the bit that we want, and we've just made it more difficult by putting it in coefficient form, but it is going to help us actually come up and equate and get an expression for delta theta, which is what we're going to want. We're also going to have this change in moment being produced as well. We're going to put this, and we could come up with an expression d m naught by d delta alpha, and we're going to put that in coefficient form as well. So we say that here the additional moment is going to be, I'll put that expression first, d cm naught by d delta A, and then multiply that by half rho v squared, no sorry, multiply that by the aileron deflection angle, multiply it by a half rho v squared s. So this expression here is the okay, so we've got the rate of the pitching moment coefficient with the aileron deflection. Again, put it in coefficient form. This is, again, just going to be a number that we're going to have for our aerofoil. Okay, so we could then equate moments. So this additional moment here and the lift dependent pitching moment, when evaluated at this point, has to be equal to the torsional reflection multiplied by the stiffness, and that's exactly what we did for the divergence before. So I'm going to evaluate moments at the elastic axis. So we've got the additional lift multiplied by EC, and then we've got this on here as well. So the sum of moments at the elastic axis is going to be equal to delta L EC plus delta M naught. Okay. Yeah, that's fine. Okay. And then I can then just use the expressions that we've just developed to put in there. So we've got expressions for delta L and delta M naught. So we can put them in here and equate it with the torsional stiffness. So it's going to be KD delta theta. Okay. I think mathematically I'm being slightly loose with some of my nomenclature here. We're going to assume that yeah, that's fine. This does work, but I've got to be careful because actually I'm not including in here the actual zero lift pitching moment. But let's pretend we've got an uncambered aerofoil and we're at zero incidence, that's fine. But this whole development still works. So again, this is the moments due to the aileron deflection, and on this side we've got the torsional stiffness and the torsional deflection. So let's put these things into the left hand side, so just taking these down and populating them in here. So delta L was these have both got half rho v squared s. Okay, I've then got the lift curve slope multiplied by delta theta, and then I've got this dCl by d delta A multiplied by delta A. And then I've got this last term, which is just this one here, dCm by d delta A. dCm naught rather. I've missed something here. This won't be correct. There needs to be a C here, and that's why this next line doesn't cancel out. So there should be a C, because remember the definition of pitching moment coefficient needs to have an additional dimension in it, which is the C, which means actually there should be a C here as well, but I can just take these both out and put them on the outside. So let's get rid of that. Let's put a little C in here as well. Okay, so that's the C going in there. And just, I know someone's going to confuse this. Remember, A is just the lift curve slope. It's nothing to do with the aileron. Okay, just the lift curve slope of this aerofoil. This still is equal to torsional stiffness multiplied by delta theta. So we've got the same problem that effectively we had for divergence. We've got delta theta on both sides of the equation. Now we can solve for delta theta. I'm just going to copy this from the notes rather than doing the rearrangement here, but we can see it's going to be, yeah, there's going to have a KD in the in the denominator, and yeah, it's going to be a fraction. And I'm just going to copy this from the notes. Being careful because I used a horrible Greek letter that I can't reliably draw in the notes, and I'm using delta A for the aileron deflection here. There we go. Okay, so that's my expression for delta theta, which we can now put into, where am I going to put it? I'm going to put it into this expression here to give me an expression for the lift now. Okay. So putting it back into our expression for delta L, we're going to get delta L, the change in lift, half rho v squared s, and then I've got a very nasty expression in here. half rho v squared s c d cm naught on d delta A multiplied by the lift curve slope plus the torsional stiffness multiplied by dCl on d delta A. So that's the rate of change of the curve, so the rate of change of the lift coefficient of the two-dimensional section with the elevator deflection divided by K, or KD rather, minus a half rho v squared S ECA. We're nearly there. All multiplied by delta A. Okay, dirty great expression that we've got here, but what we can see is that the additional lift, or the additional lift that is generated by the aileron, is going to be a function of the aileron deflection angle. But we're also going to we've got a couple of horrible things in here. We've got the flight speed squared in both the numerator and the denominator of this expression, and we've also got it on the outside here as well. So it's got the same denominator as the divergence expression. So at that point we've got divergence anyway, so we don't care about what happens to the delta L, because that's just the case where we've got lift tending towards infinity, which clearly we don't really have, but shows us when divergence happens. We can also have on here the numerator can be 0. Okay, so when the numerator on this is 0, that's when we have aileron control reversal. And the reason why that can be 0, let's just think about this term here. D cm naught on d delta A. So with our sign convention, and just in general, there is no good sign convention for control surface deflections. Varies from manufacturer to manufacturer, but we've said that we just defined delta A as being a positive deflection. So that means that that's going to cause an increase in lift. It would also cause an increase in nose down pitching moments. That's going to be a negative cm. So dcm by d delta A is going to be less than 0 for our expression. Okay, so we've got something negative and then something positive. So that's going to be something that can be at some point when the flight speed can be equal to 0. Okay. Let's just put this here. So the whole term there, half rho v squared SC dcm naught by d delta A multiplied by A, that's what I mean by the bit that I've just circled. This term will be negative. Hence, reduce delta L with the flight speed squared. This term here is the bit that gives us control reversal. Okay, if we just had a rigid aircraft, then this whole expression would simplify a lot more, but it's this bit here that gives us control reversal. So when the numerator is 0, this is the control reversal speed. Or the critical aileron control reversal speed, I think I called it earlier. It doesn't really matter, it's just the speed at which the controls are reversed. So that's going to happen when this whole top bit is equal to 0. And we're going to call this VR. VR's got about 1,000 uses in aerodynamics. Sometimes it's resultant velocity. We're just going to call this one here as the control reversal speed VR. Okay, so that's going to be half rho VR squared SC. Let me just think about what I've got in here. dCm naught d delta A multiplied by A plus KD. Okay, so when that whole numerator is equal to 0, that's only possible at the control reversal speed. We can then just solve this expression for the control reversal speed. Okay, so the control reversal speed is the square root of torsional stiffness. This should be KD. KD, DCL on D delta A, the rate of change of the lift coefficient of the wing with the aileron deflection. Half rho SC, I automatically wrote half rho V squared because I'm used to writing dynamic pressure, but the V is what we've just solved for. Wing area called rate of change of the pitching moment coefficient with the aileron deflection. This is going to be a negative number, so this whole expression is a positive quantity because we've got a negative numerator, and then we've got this lift curve slope here. Okay, so just remember that one's going to be less than 0. We can then define the aileron effectiveness as a measure of effectively how much additional lift is generated compared to the rigid wing. Okay, so if this expression weren't in here, that would give us the actual additional lift given by the excuse me, given by the rigid wing. In fact, it's not just if that term wouldn't be in there. I'm not. Let's say if it would be if KD was equal to infinity. Okay. We don't actually have a symbol for aileron effectiveness, we just say aileron effectiveness. Okay, it's going to be a non-dimensional quantity. It is delta L. So this top delta L is the one that we just developed. It's that one, okay, the actual additional lift generated, versus what would be present on the rigid wing. And this one here is just going to be half rho V squared S multiplied by DCL D delta A multiplied by delta A. Okay, so that is just however much the lift coefficient increases because of the rate of change of the aileron multiplied by the dynamic pressure wing area. Okay. There's some further expressions we can develop from this, and I'll leave you guys to look into the accompanying notes that we can get a measure of the aileron effectiveness. I want you guys to go through the rest of this in the notes because I can see there's just a lot of going through algebra here, and I trust you guys to do this in yourself. Make sure you understand how equation 5.28 occurs, and if you're really tenacious, show me how you get equation 5.29 in the notes. Okay? And I want you to message me on Slack when you've got to this point. Okay? If you can get equation 5.29, I'll be impressed at that as well. Okay? That's a good bit of algebra. I'll consider a complete bit of getting the Aileron effectiveness as equation 5.29 as a little bit of extra credit if anyone wants to get that done. Okay? That is a lot we've covered today. We went through the physical basis for control reversal, and we've now developed a model for it. So we've determined the control reversal speed, and we've shown that it is just this expression here. It's going to be a function of however much additional lift is generated multiplied by the torsional twist, and then however much additional moments generated as well. Okay, so this whole expression here, we're going to be going through some problems next week that show us actually how we use these to develop solutions for real aircraft problems. Okay, hope you guys are having a wonderful week. That's it for me this week. I'm probably packing up my house as you guys are watching this, and I will have a review later this week at a date, time to be determined. Look forward to seeing you guys there, and I am going to do a review of the entire course over the next few weeks, including lots of example problems that you may be facing in your final. Okay, take care guys, see you all soon.